Lecture 20. So in lecture 19, I explained what a multiple regression is and what types of questions that we want to address when we have multiple regression. And I demonstrated a multiple regression with this data here that had the weight of the fish and the prediction, and I want to predict the weight by uh, using the data of the length, height, and width. And the result came out to be like this one right here, where the adjusted R square was 0.936. And uh, I tried to explain adjusted R squared in several different ways, but I guess at this point you should try to remember it as just one sound definition. So think of it like this. What is adjusted R squared? That is the uh, percentage of the variance of the data due to the regression. Okay, so that's how you can say it. Okay, yeah. All right, and that being 93.6% means that it means that 93.6% of the variation of the data can be explained by the regression. That's what it means. Okay, I like that better. Okay, so uh, okay, so maybe I should write that here. So I was explaining the okay. So this R squared, which is called coefficient of R squared, is called the coefficient of determination, and it is the percentage of the variation of the data that can be explained by the regression. Okay, so it is the percentage. So let me make this in red. So looks important. Okay. So R squared is the coefficient of determination and is the percentage of the variation of the data that can be explained by the regression. And of course, that being 93.6% means that this regression is doing a great job in explaining the data, right? If this adjusted R squared is small, then uh, even if you have some correlation, uh, it might not be doing a good job in explaining the variance of the data, and you may have to look for some other additional reasons why the data is varying. Okay. Okay, and I also said that because the p-value is so low, that also means that this is the the multilinear regression is, well, let me just go to the no, no, that's not what I wanted. Sorry. Okay, so the the overall significance of the prediction is given by the significance f, and if that value is closer to 0, then that's a good sign. Okay. Yeah. So if the p-value is less than the significance level, we say that the independent variables that we use in the Excel spreadsheet that we just used, those are the length, width, and height, right? So those, when taken together, are useful in predicting y. Okay. So that's the alternative hypothesis. Okay. The null hypothesis would be those three variables, when taken together, is not good for predicting y. Okay. All right. And then I kind of stopped there, and now let's continue our discussion. And the goal for us is to look at various values that we have here and be able to understand what each of these numbers mean and how you can calculate some of them. So for example, uh, some of the questions might have exactly this table right here, but it's going to have these values empty, and you have to find them out. Okay, so that's one thing. And also, it might ask you what these mean. Right. Okay, so let's try to figure this out from the table. First of all, uh, degrees of freedom of the regression is 3, and this is related to the predictor variables. Okay, how many predictor variables are we using? What are the predictor variables you're using here? We're using 3, and what are those? Length, height, width. So those 3, right? So because we are using 3 predictor variables, that number is 3. So degree of freedom of the regression is the number of predictor variables. Got that? Okay. And then the the degree of the degrees of freedom of the residual is what we usually talked about as degrees of freedom in regression. Okay, so in the single linear regression, which is single linear regression just has one predictor variable, right? A multilinear regression is actually just a single linear regression if you just have one predictor variable. Okay, now who can tell me the degrees of freedom of a single variable simple linear regression? Okay, how do you calculate the degrees of freedom of a simple linear regression? N minus 2, right? Yeah. And I'm telling you that in general, the degrees of freedom of the residual, which is the n minus 2, in general, if you have many predictor variables, the formula is n minus 1 minus the number of predictor variables. Okay, simple linear regression has just one predictor variable, so that's why it's just n minus 1, which is just n minus 2. Okay. Uh, all right, and then the total regression is just simply the sum of these two, and because this 31 is n minus 1 minus 3, if you add up these things, you end up with n minus 1. Okay, so the total degrees of freedom would be n minus 1. Okay. All right. So let me go to the slides and make the remark here. All right. So regression degrees of freedom is number of predictor variables, which we are going to state as degrees of freedom of the regression. And I think it's better if you just say degree of freedom of regression. And that's equal to the degrees of freedom of the residual. Okay. And the total degrees of freedom is equal to just n minus 1, okay, which is the sum of these two. If you add degrees of regression plus the n minus 1 minus degrees of regression, then these two things will cancel. I think I should use capital here. This one and this one will cancel, and it leaves you with n minus 1. So that's what we call the degrees of freedom total. Okay, total degrees of freedom. Let me make this smaller. 24. Okay. And then knowing that, here's a formula that could be used to find the adjusted r squared from the given r squared. Now, this will be provided to you on a formula sheet, so you don't really have to memorize it. However, just keep in mind that if you work this out, you'll see that the adjusted r squared is always less than r squared. Okay, that's because the total degrees of freedom is always more than the degrees of freedom of residual. So if you compute this, this will be a bigger value than the 1 minus r squared. Okay. All right. So back to our chart. Okay. So we were talking about the degrees of freedom. So everything good so far? Right. The sum of squares are the sum of squares of the values. So for each x1, x2, x3, in our case, it's the length, width, height. We take the value minus the average squared, and you add them up. That's the sum of squares. Okay. And then you can do the same thing for the residual. Now the average of the residual is always 0 because that's what multiple regression does. It makes it to have average 0. So it's simply the residual value squared, or you know what residuals are, right? That's the difference between the actual data value and the prediction y hat value. You take the difference, you square them, you add them up. That's the sum of squares of the residual. And total will be just sum of these two. Okay, so usually this will be provided. Now, here's the important part, okay? Mean squared. So SS means sum of squares. MS means mean of the sum of squares. So that means when you take the mean, you're taking average of something, right? So you have to divide by something. And what do you divide? If you divide the sum of squares by the degrees of freedom, you get the mean squared. Okay. So for example, let me show you how this 27884 is obtained. So let's take a calculator. What you can do is you take the sum of squares of the residual 86305, and you divide it by the degrees of freedom. Sorry, you divide it by degrees of freedom, which is 31. And the answer is 2784, exactly same as this one, right? The decimals don't match because I didn't type in everything. So but if I typed in everything, it will be like this, okay? So that's how you get the mean squared. Is that good? Right. That will be a kind of a problem that could be on the exam. This portion will be left blank, and you'll have to figure that out, okay? All right. How about this F value? Well, so what you want to do is to reduce this residual, right? If this value is small as possible, if the mean squared is as small as possible, that means you've succeeded, right? The linear regression is doing a good job. The multiple linear regression is doing a good job if your residual is less, because residual is the error of your prediction. And what you do is you take the mean squared, which is the sum of the regression. And I want to say that if the predictor values vary a lot to begin with, it's harder to reduce the residual because like your input is varying a lot, so your residual could also vary a lot. So what I'm trying to say is that even if you have the same regression, exactly same regression. If your x points are varying a lot, right, then of course your y residual will also vary a lot. Does that make sense? Yeah. So you want what you want to do is you want to reduce the regression ms while increasing the no you want to uh, you want to reduce the residual even if this is quite big. Okay. So what you do is you take the ratio of these two values. So the f test statistic is the ratio of two sum of squares, or two mean squared. Okay, that's what f distribution is. Okay, and mathematicians have computed this distribution for various values of degrees of freedom. Now, this f distribution is quite complicated. It's more complicated than the chi-squared or the normal distribution or t distribution, because it has a lot of parameters. So think about the following. How many parameters does a normal distribution have? You just need to know the mean value and the standard deviation, and that's it, right? In fact, if you set the mean as 0 and standard deviation as 1, you just have one distribution, which is the standard normal distribution, right? Uh, and then when you go to chi-squared, it gets a little more trickier. Chi-squared tracks down what happens to the test statistic if you just take a mean squared, just sum of squares, but you take the mean and you just want to see if that's a big value or a small value. And for that, the distribution behaves differently depending on what's your degrees of freedom. So the degrees of freedom becomes a parameter. So different values of degrees of freedom will give you different chi-squared distribution. So your table, uh, when you use the table, you actually have to look for the degrees of freedom. Okay. T distribution also has degrees of freedom there. However, the F distribution is the most complicated distribution that we've ever seen, because uh, it deals with the ratio of two sum of squares, and the top one has the degrees of freedom, and the bottom also has the degrees of freedom. So you have 2 degrees of freedom, and because of that, the chi-square table becomes very complicated. So I have an example in the slides. Here's an example of a chi-square distribution. You need to provide the numerator degrees of freedom and denominator degrees of freedom, and you get the critical values, but the critical values are only given for a certain significance level. If you change the significance level, then you need to look at a whole different table. So you can kind of see that F distribution is a lot more confusing to use, right? Okay, so that said, let me summarize everything that I've said so far, because I've said a lot of things so far. So what was I saying? What's the degrees of freedom of the regression? Huh? Yeah, but what does it mean? How many? How many predictor variables you have, right? Good. Okay, what is the residual degrees of freedom? It's n minus 1 minus the number of predictor variables, okay? So I have 35 data sets, and 35 minus 1 is 34, and you subtract 3 from it, you get 31, okay? Total degrees of freedom is the sum of those two, okay? Sum of squares, I think I explained that. How do you get the mean squares again? You divide the sum of square by? You divide the sum of squares by? Degrees of freedom, okay? You divide this value by this value, and that's how you get this, okay? Now, how do you get the F statistics again? Oh, MS is simply this divided by this, okay? SS divided by this, okay? This divided by this, right? Okay, and F is simply this divided by this. Is that good? F is this divided by this. So you get the F statistic, And then this value, the bigger it is, the less probability it will have. All right. And let me show you how to get this significance f. That's the p-value. To get the p-value from the f-test statistic, what you need to do is you have to go to the calculator, and you have to use the, let me put it over here. You have to use the FCDF. So here's the FCDF. And let me show you how you get this 3.01 e negative 19. That's e negative 19 means 10 to the negative 19th power, so that's a really small number, right? Okay, so what we want to get is, I can't draw the F distribution graph here, but F distribution graph looks something like that, and you want to know the area right side of this value. That's your p-value. So you want to put in 167.8335 for your lower, whatever value you get here, you put it here. And from here, you have to go to infinity, but you know, infinity is not, it does not exist in a calculator, so you have to just put some huge number. What number should I put in? Million. Okay, I like million. Okay. You can actually get by using 1,000. These distributions, they drop so fast. At 1,000, it's almost zero. So yeah, but million is fine. Okay. All right. Now, tell me what to use for the degrees of the numerator. Degrees of freedom of numerator. 3. How about the degrees of freedom of denominator? 31. Okay. And then we paste this, and that gives you 3.01059 e negative 19, exactly same as this one, 3.01 e negative 19, right? So you see that they agree? Okay. So that's how you get the p-value just from this, okay? So let me warn you again, you will have a question that looks like this, where you're only given this part and these are put blank. This is also blank and this is also blank, and you have to figure out the values yourself and put them in, okay? And on the exam, yes. And the way you should do it is this value is this divided by this value is this divided by this, f is this divided by this, and then this value is, you use FCDF with this as the beginning value, and infinity is just 1 million, and then you have to provide the degrees of freedom of the numerator and the denominator, and it will give you this. Okay? Yes? Because the graph of the F distribution is somewhat like the chi-squared. It looks somewhat like this. It starts at 0, and gee, I can't draw it, but it's like this. And then the p-value is the right tail. We're really doing the right tail test for this, because it becomes more and more significant if this divided by this is bigger. Okay, so we just want to know how significant it is by looking at how big this is. So you want to see the total area right side of this value. Okay. Yeah. Other questions? Okay. Now let's talk about the standard error t-stat. Okay. So uh, so each of these values also have p-values, and here you see that height alone is very significant, but 0.12 and 0.2 are both above 0.05. So if we have our significance level at 0.05, that's not going to be very significant, right? So in fact, if you have predictors that are not very significant, you can just drop them and then go with just the remaining ones, and you'll still have somewhat very significant ways to get it, okay? So let me show you how that one works. So suppose suppose we do the multiple linear regression. Actually, we're going to drop the length and the width, and that would mean that I'm just going with the height. So there won't be any multiple regression anymore because you just have one predictor. That's just a simple linear regression. But anyways, let's see what happens if I just go with the one significant predictor, okay? So let's go to the data analysis, choose regression. There's a regression, choose regression, okay. And then the input y range, we're trying to predict this y value, right? So you have this much, and then for the input x range, we want height, just this only. Okay, and then our data has labels, so I have to put the label there. And then these are all additional plots, but let's not plot anything. Yeah, let's just run it, see what happens. Okay, so I didn't produce any graphs, but as you can see, your r squared and adjusted r squared right here is 0.928, which is 92.8%. So with just one predictor, you're able to achieve the almost the same adjusted R when you use three predictors, right? And you have even more significance. So in that case, uh, it's better to just use the height. Okay, so that's a process that you want to do whenever you do multiple regression. So I've explained here. So note each predictor has a p-value. We want to use the least number of variables to predict the value of the dependent variable. Some predictors contribute more than others, and we use the p-values to determine which predictors would give the best regression equation. And we eliminate any variables with p-value greater than the given significance level. Only the ones with p less than alpha are kept. And so we can say that in our example, the height was the most influential predictor variable. Okay, so that's another question that you can get. So another type of question you can get is you might be given this portion of the graph, the thing, and you might be asked, what's the most significant predictor? Okay, and a lot of times people would look for the wrong column. They might look for the coefficient and say, hey, that looks like very big, more than the other one, so I'll just say intercept. But actually, that's true. This is the most significant. But this is not a predictor. Intercept is not a predictor, so you can't put that. The predictors are length, width, height, and width. And among them, which one do you choose? You choose the one with the least p-value. Okay? You do not choose the one with the biggest value in other columns. You just go to the p-value and you choose the one with the least value. Okay? That's what you have to use for the most influential thing. Okay? All right. And then there's also the lower 95%, upper 95%. Yeah, I don't know why it's repeated twice, the same thing. But let's just delete this. It's not really important. So if I put 31, okay? So second vars inverse t, and 1 minus 0.05 divided by 2 is, I want to put this in there because I want the 95% critical value, and our degrees of freedom of the residual is this. So you need, oh, so that's what we have to multiply, sorry. So you have to find the t critical from this. I thought this value was this given value, but it's not. You have to calculate separately. So let me calculate this again. You have 62.8 plus 16.68 and then times 2.039. Then you get 96.8 something, which is this value, right? So that will be another type of question that you will have on the exam, okay? So you might have these left blank, and you're only given the standard error and the coefficients. If these are given, then you have to use the inverse t to find the critical value and multiply that to the standard error, and that this value plus or minus the standard error times the t critical gives you the upper bound and the minimum bound. So that's how you get the confidence interval. Now that one, I think we've done several times, so you kind of already know how to do that. Okay. All right. Let's see. And I think I explained everything regarding this table. So when you see this table, you should be able to read everything. I didn't explain what this t-stat is. I actually have no idea. I don't how this one is obtained. Uh, no. I know what it is. Okay, okay. So this t-stat is actually the value of the t-test statistics used to get this p-value, right? And this one, uh, it, it it has a different calculation which I can't go over. Okay, so I see what that is. Okay, so sorry. All the confusion was that I thought this was the critical value of the t, but that's not. This is the t-test statistics to find the p-value of each of these predictors. Okay, all right. Sorry about that. Okay, all right, and then you have all these residuals. That's it. Okay,